And that's what we're going to talk about in example 2. So example 2 says find the volume of the solid by rotating the region bounded by y equals x squared, y equals 4, and x equals 0 around the y-axis. So again, let's see what the heck's going on so we can see what's actually happening. So first off, let's just graph a region. So, and we want it from x equals 0 to y equals 4. 4. So we plug in 0, we get 0. Plug in 1, we get 1. Plug in 2, we get 4. So there's our portion. So if I wrote this now, just like kind of like this one, so if I rotate this way, notice it's going to be mimicry on the other side, right? So it's basically the same parabola on the other side. So I'm rotating it this way. And again, I also end up getting another top. So now the only difference is the top is now on the y-axis instead of the x-axis being on the side. So therefore, when we correspond to our circle is going to look like this. So again, this is the center, and we're going to find the radius there. Okay. So therefore, a radius is from here to here. So remember, this is going back a section, right? Right minus left. The only problem is, unfortunately, if we do take the integration with respect to y, that means we have to actually solve for y. So we're going to have to tweak this around. So solving for y here, or solving for x here, gives you the square root of y equals x. So a radius is the square root of y in this case. Because again, you're subtracting 0. So that minus 0 is just 0, just we did up here. So now we have that. Now we can take the integration. So our volume is from 0 to 4. Again, right, not from 0 to 2 here. We're rotating on the y-axis, so we're going this way. Right, so this is perpendicular to the y, so we have to integrate with respect to y. Of pi r squared. And again, I'll just put this into its exponent form. And notice those cancel, which is super nice, right? So it's just the integral from 0 to 4 of just y. So integral of this is going to be y squared over 2, evaluated 0 and 4 pi. So we plug in 4. This is going to be 4 times 4 is 16. 16 divided by 2 is 8. So this is going to be 8 pi. And then 0 is just 0 itself when it comes to it. And there is our area. So one thing when it comes to the washer method, and for all methods we're going to talk about in this section, is you got to make sure, again, it's always perpendicular. So remember, this is perpendicular to, the radius is always perpendicular to what you're being rotated of. So this is why over here, this is perpendicular there. Right? We're not rotating this way, we're rotating that way. Same thing here, rotating this way, so therefore it's perpendicular to the axis, or the axis you're actually doing it. And that's the reason why we had to find, solve for y here, or solve for x here, and we convert our bounds of integration itself. Okay, so again, like I said earlier, we're talking about 3 different methods. This is the first one. It's called the disk method. The next type of method we're going to talk about is called the washer method. Now, if you wonder why is it called a washer method, we'll talk about that as to why that a little bit. It's not like you're like washing clothes or something. It's a little different. So if you work on the yard or anything like that, you'll know what I'll talk about in a little bit. So this is called the washer method. Right, so the concept of the washer method is kind of like this. So let's suppose we have this function f of x, and this is g of x. And this, again, this is from a to b. Okay. And what if I rotate this about the x-axis? So when I rotate, right, so that means I'm rotating this way. And The problem is, again, this is the area we're rotating. So notice automatically when I rotate this way, right, there's a little piece here that's actually not being used, right? It's empty. Unlike when it came to the disk method, where the entire thing underneath the curve is being rotated. This one, however, there's a little piece there that's missing. So when I rotate this about the x-axis, so I'm going to rotate it that way, we actually get something like this. It's kind of like a funnel. So there's empty hole in the middle. Where this is now empty and not a solid funnel. Going this way, it goes down, 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 down. So it's kind of like, if you want to think of it, like the little shading region goes portion there. Now if I do the circle here, I have my regular circle. However, I'm missing this piece here, so it's actually missing that there. Okay. So again, if I push this out, I actually have a disk within a disk. And the region we actually care about, or the area we actually care about, is the outside portion. So if you work in construction or you build some stuff, the reason it's called a washer is because this is actually a washer. You put this in between nuts and bolts. That way, the pressure isn't drastic. It builds some pressure there. That's why it's called a washer. Usually in silver. So that's why it's called a washer. So essentially, we want to find the area of this stuff here, right? And then relate it back to these kind of stuff. Now the good thing is, right, we kind of already know how to do this, right? We know how to find the area of the entire portion. So let's say A area total is equal, again, pi r squared. Let's say, where r is, again, the total area there. And we want to find this region. So you guys agree, right? The area of the region we want is the total area minus this little small patch, right, that's empty. So we'll say that. So area of, let's say, area 1 is pi r1 squared. So how to find the region we want? We just subtract them. So the actual area we're looking for is the total area minus the area we don't want. And that's essentially exactly what the washer method is all about. It's essentially outer area minus inner area. So when we do this portion, the area of the entire portion is going to be pi times the outer radius squared minus pi times the inner radius squared. Because that's exactly what the areas are, right? If you do this minus this, that's it. It's just outer minus inner. So therefore, our volume is, again, from A to B of the subtraction of the two areas, dx. So again, this was the reason why I call this a little tricky, because you got to identify which is the outer, which is the inner, and then square them and subtract them, because if you flip them around, you do actually get a completely different number. So that's what you got to be careful of itself. So let's try an example so you can see how this will actually be applied using our washer method here. Okay. So find the volume of the solid obtained by curves y equals x and y equals 2x